That is Q by 2 into V. Why? Because of here V equals to Q base. So this is the equation. How do you got? Or else, what is Q? Q equals to CV. Substitute here. That equals to CV by 2 into V. That is CV. Is it clear? Okay. This is the case you need to know that. Most important short question. Very, very, very most. In objective, while you are going to write the competitive exams, there also they are going to ask what is the capacitance and energy stored in a capacitance of a capacitor plates. That is of CV square. That means you need to understand that how many forms are there. Is it clear? How many forms? This is the one form, another form, three forms. Okay. So these are the three forms. Next one. Combination of capacitors. So capacitors which are connected in parallel. Okay. I'll practice it. diagram. మొత్తం 4 డయాగ్రామ్ నేను అడుగుతాను చూడకుండా ఏమో. Again, after this period, project is also there. So 2 o'clock ki mala digital dantlo meeting waters. So to find the capacitance here from this figure, capacitors which are connected in parallel. So that capacitors which are connected in parallel. So that this is the first capacitor, this is the second capacitor, third capacitor. Between potential difference is applied. Okay. So that here what is the equivalent capacitor which can gives you that the parallel combination of these single capacitors, which is indistinguishable and their electrical instruments. So these three which are connected to a terminals of small a and b. Where is a? This is a and this is b. Okay. So what is the potential difference across these capacitors? So here the upper plates which are connected to the terminal A and the lower plates which are connected to the terminal B. And what is the relation? C equals to Q by V or Q equals to CV. Okay. So what is the first capacitance? C1V. Why? Because of here the potential difference is same. Not C by V1. C1 by V. C1 V1. Okay. Q equals to CV. Or capacitance formula C equals to Q by V or Q equals to CV. For first capacitor, C1V. Why? Because of potential difference is same. Similarly, C2V, C3V. Okay. What is the total charge? Q1 plus Q2 plus Q3. By adding these three, C1 plus C2 plus C3 and V. So the capacitance C equals to Q by V. That is here print mistake. This is the Q value. C equals to Q by V. That what is the Q and D? that equals to C1, C2, C3, C1 plus C2 plus C3 into V divided by V get cancelled. Remaining total capacitance here print mistake. Okay. So the total capacitance is next when capacitor which is connected in series, you can see series is different than the parallel. So these are parallel and here is which is in series. So same thing, we are considered here three capacitors which are connected in series. But the thing is that one plate of the first capacitor which is connected to the plate A and the last plate of the capacitor which is connected to plate B, okay, terminal B. So in this here between capacitor plates, the potential difference which may gives you here one is V1, similarly other plate is V2. So in series, the potential difference which may here which can changes here, okay, potential difference which can changes, whereas in parallel potential difference remains same, but here changes. So for this case, the three components which are connected in series means C equals to Q by V or Q equals to C. So here V1 from this V equals to Q by C. V1 equals to Q by C1, V2 equals to Q by C2, V3 equals to Q by C2. Whereas the potential difference for the combination which is in series means total potential difference V1 plus V2 plus. Okay. Substitute here Q by C1, Q by C2, Q by C2. When Q is common, 1 by C1 plus 1 by C2. This is the V naught total. But what is the formula? C equals to Q by V. So Q by what is V? Q of 1 by C1, 1 by C2. Q get cancelled. What is that resultant capacitance which is connected in series? This is the answer. Final answer. So one of the best example application when two concentric spheres, okay, which are arranged, the two spheres which are arranged concentrically. This is the figure. So that one of the sphere radius is small a, other radius is small b. You can see the figure. So this is the case. So outer sphere radius which is greater than that of the inner sphere. Okay. So here, what is the potential difference between these two means? If you want to calculate the potential difference between these two, again you need to imagine another concentric sphere which is showing like a here not at plus, yeah, minus. The symbol is representation. So here dotted lines which is representing there only if you choose a point, that point is representing K, there you need to calculate the potential difference. So that UDR, but what is the equation here? Potential difference. Potential difference equation and V equals to 1 by 4 pi epsilon r into Q by R. Okay. So here integral dr, not r square. So by integrating dv equals to this is the equation. Okay. So there is a medium is there here. That is u by 4 pi epsilon r k integral b to a. It is 1 by r into dr. So that dr by r minus 1 by r. Okay. So that by substituting limits, you can have this equation. So after that, what is the capacitance equation? Q by V. What is Q value? Q is this. What is V value? This one, which you have been calculated. So that the sum of the Q get cancelled. By simplifying this, you will get 4 pi epsilon naught K AB by B minus C. So, farads. If two spheres are surrounded by air, for air K value is 1. 8.85 into 10 power minus 12, which is related to epsilon naught. This is the case. Most important. So this is the cylindrical form. Capacitance of the cylindrical capacitor. So a metal cylinder which is placed coaxially inside a hollow metal cylinder of large radius. The space between the cylinders which is filled with a dielectric material. So that what is the dielectric constant? K. K. K is a constant, that is dielectric constant. So in this case, the best example is a submarine cable is a practical example for this cylindrical condenser. So in this, the inner conductor is a copper cable and seawater is the outer, that is earthen cylinder. So the insulating chain or a polystyrene forms the dielectric between these two. So that let us consider that B is the radii of the uh, small b. Inner sphere cylinder, where small a is the inner and b is the outer cylinders radius. Between them there is a dielectric constant. Here you can see. So this is the B and this is the A. So that what is A? This one. The radius is A. Which one is B? This one. Which is a B. So between them, dielectric constant. Okay. So you can imagine that where the capacitance. So outer sphere is positive. Inner sphere is negative. That means this positive and negative charges which are accumulated on the surface of the here cylindrical spheres of the capacitor. Okay. So you can imagine a Gaussian surface that is to be intimating that dotted lines which intimates you here a Gaussian surface. So there only, if you want to calculate the intensity of the electric field, which is gives you the intensity of electric field from the Gauss theorem, that is surface integral E dot is equals to Q by epsilon naught. By implementing this, you can have 2Q by 4 pi epsilon naught KR. So what is the potential difference between outer and inner cylinders? So what is the equation for potential? 1 by 4 pi epsilon naught into Q by R. Okay. So at what distance magnitude of charge is to be considered? That is the charge is written here, 2Q. Okay. By simplifying, Q by 2 pi epsilon naught K log B by A. So what is the basic formula? Capacitance equation Q by V. So you know the V value, substitute here. Q by 2 pi epsilon naught K log base C B by A. So by cancelling, simplifying this equation, 2 pi epsilon naught K 2.303 into log base 10 B by A. Next is the cylindrical sliding condenser. Sliding one to other, how it is jumps. Okay. So these questions are asked many times. You can go through this. Next is the parallel plate condenser. The concept of capacitance and potential, which was discussed in the previous unit, C equals to Q by V. One plate is there that is having a positive charge. Other plate is there that is B, a negative charge. These two plates are separated by a distance small d. So in this, if you want to calculate the potential difference between these two plates, which may gives you what is the integral form and electric potential ki electric field ki V equals to minus integral E dot dr. Okay, so this is the integral relation between the potential difference and electric fields. So in this V equals to minus E dot dr, or else what is E value, electric field value between these two plates. So 0 to d to 0 sigma dr by epsilon naught k d sigma by epsilon naught k. Where sigma is the surface charge density. Charge per area, charge density. Substitute here. So what is the V value? Vd by epsilon naught ak. So that from this equation, you know the relation. What is E? E equals to Vd by epsilon naught ak. Again, we are substituting V value. C equals to Q by V. That is epsilon naught ak by d. Q value. That is V value. So after that, we are getting if dielectric constant value, if it becomes 1, that is K value 1. So in this case, C equals to epsilon naught A by D. Other thing is that here, if a dielectric slab is filled between these two plates of the capacitor, so how it is going to be changing? One plate is negative charge, other plate is positive charge. So these are to be separated by a distance here. So other plate is grounded. So in this case, applying the Gauss theorem, that is, sir, how this equation came here? EA, surface integral E dot ds. E surface integral ds. Very, very simple. But V equals to minus E dot dr. Substitute here, what you will get. So C equals to Q by V. Substituting, you will get this. So see here, between the plates of the capacitors, a dielectric slab of thickness small t, so very small t here, small t, thickness, okay? If it is here introduced between the plates of the parallel plate capacitor, how the capacitance of the capacitor is going to be changing here. So that from the figure only, one is having surface charge density is positive rho, other is having surface charge density is negative rho, and these two plates are separated by a distance small d, and the thickness of the here dielectric slab is small t, and from the first plate to the upper surface of the dielectric slab distance is d1. Is it clear? So from the figure only we have it discussed. So by using and doing the calculation, you may have C equals to epsilon naught A T by D of D minus T. This is the variable condensers. So the series of plates sensor. Okay. So this is the variable condensers. Types of condensers. This is the variable condenser. Variable means you can able to change the capacitance of the capacitor. And also fixed condensers is also there. And God ring condensers, standard condensers. This is the God ring standard condensers. The force between these two. Energy. Half CV square. Next. This is a very, very important short question. Dielectricity. An atomic point. So dielectric means which is nothing but which is having a higher resistance. That means a material doesn't offer any current at all. Then that type of material you can call it as a dielectric material. Okay, Andy? So here, if you place the dielectric in an electric field, so here the molecules of the dielectric, like water, which have a permanent electric dipole moment. So that what do you mean by dipole? What do you mean by dipole here? The magnitude of the charge which are separated by same two two or more charges. Di means two here. The same and opposite charges which are separated by distance is dipole. So what is the dipole moment? The dipole moment is P. The product of the magnitude of the charge to the distance between them. Okay. So magnitude of the charge is Q and the distance between them is 2L. So dipole moment is P. P equals to Q into 2L is the dipole moment. Okay. So H2O molecule is having a permanent electrode dipole moment. So permanent electric dipoles of dipole moment, which is denoted by capital P, which can tends to align themselves with an external field. So here, by applying an external field, that means what type of field? Electric field. If there is a field, there is a charge. If there is a charge, there is a line of force of field. Okay. So the alignment of these polar molecules, which is in the direction of the electric field. At what, in which direction the electric field is applying? There only the alignment of the dipole, the molecules which are turned into the direction of the electric field. Okay. But it will not be complete due to the thermal agitation. Thermal agitation means here to vary the temperature. But the degree of the alignment will increase if the electric field is increased or the temperature is decreased. Okay. Coherent. So here you can able to see the what is the first picture? Polar molecules and electric field. Without electric field. Very, very important. This portion is without electric field. So that here minus and this is the plus. Okay. So this is the dipole. How the alignment? That means here how these are aligning here randomly zigzag here in downwards. This is an upwards. And downwards and downwards and this direction downwards like that. So that different directions alignment is different. Okay. Without electric field, that means random variation is to be observed. Whereas if you apply an electric field, see that difference. See the difference. What is the difference? You can observe. Okay. So that yeah, the orientation should be like this. The alignment should be like this. Okay. So the alignment should be like this. Okay. Like that. So here, irrespective of the nature of molecules, whether a molecule is polar or non-polar, there will be some induction when they are placed in electric field. Before placing this in an electric field, you have been imagine that the orientation of these dipoles are in different, randomly placed. But when you apply an electric field, external electric field, so that the alignment of these, which are aligning in which direction the field is to be applied, in that direction only the orientation of these dipoles are to be observed. Is it clear? So this is a very, very important. So here the external field will be tends to separate the net negative and positive charges in an either it is atom or molecule. There should be a induced electric dipole moment is present as long as external electric field is there. Okay, induced. So that by using the parallel plate condenser, by carrying a fixed charge Q1 and not connected to a battery, and which may provides an external electric field. See here. Okay. So a dielectric slab which is placed in the field here before, I will zoom in. You can see. So here before placing the dielectric slab, this is after placing the dielectric slab. And here this is a V naught potential difference. Here VD dielectric slab is if it is placed between the plates of the condenser. So you can see here. Okay. So from this, the effect of the field on the slab is that the center of positive charges entire slab, which is separated from the center of negative charge. But the slab as a whole remains electrically neutral. So a pile of positive charges rest on one face of slab, while other face consists a negative charge, and no charge remains within the slab. Therefore, the positive and negative charges must be equal, since the atoms and molecules which are electrically neutral. So what is the displacement of the electrons in the dielectric from their equilibrium position, which is less than the atomic diameter? You need to remember this. Okay. So here, like that, the resultant electric field. So the induced surface charges, which is always appears in such a way that the electric field is due to them is E prime, which is opposes the electric field E naught. Okay, external electric. So the resultant field is that E naught plus E prime, where is E prime is same direction as E naught, but it is smaller. The induced charge in the dielectric, which is due to external field, which tends to weaken the original field, and the field reveals itself a reduction in the potential energy between the plates of the charged capacitor, so that if dielectric slab is introduced, what is the dielectric constant, which is the ratio of the here electric field which is in a free space to the media, or else the potential, the ratio of the potential difference between the plates when it is in the free space to the media, that is E naught by E or V naught by VD, that can gives you the here dielectric constant. So many dielectric constant, variation of the dielectric constant you can observe here. Okay, different substances having different dielectric constants. So for example, mica is there 4.6. Okay, for air, what is the air? Dielectric constant is 1, and whereas the here Teflon, nephron is also to be considered here. That is the case. Hydrogen is also 1.0026. So effect of dielectric slab on the capacitance of parallel plate capacitor. If you introduce between the plates, parallel plates of the capacitor, a dielectric slab is introduced here. How the capacitance is going to be varying here, that you need to calculate. But before calculating the capacitance of the parallel plate capacitor, you need to calculate the what is the potential difference value between them. Why? Because of here the equation part as per the definition, which is going to be showing that C equals to Q by V is there. That's why you need to calculate the V value. Later on, in the formula, if you substitute, you may get the what is the final equation. That is case. Here also electric displacement, electric polarization, and electric field. Okay. So what is electric polarization? The induced surface charge per unit area of the surface. Induced surface charge per unit area. That is Q naught by A, which is denoted by polarization is P, electric polarization. As well as here, if you introduce a dielectric slab between them, which is having the thickness is small d, that is also to be given out here. But here, if Q and Q1 are the free and induced charges on the plates, let capital A is the area of the plates and the separation is small d, then the relation Q by A equals to epsilon naught into Q by K epsilon naught A plus Q1A, which can be written as Q naught Q by A equals to epsilon naught E plus P. Why? Because of here P equals to Q1 by A. But you know the basic relation, that is what is the relation between the electric displacement, electric field and electric polarization, that can gives you D equals to epsilon naught E plus P. But whereas the D is the displacement current, here that can gives you here Q by A by substituting and simplifying. And this is a very, very important figure. You can see here. I can conclude within 2 minutes. You can see here upper portion. So this is the one plate, first plate is having a positive charges, and this is the second plate. This is having negative charges on it. So here between them, a dielectric slab is to be introduced here. Okay. Whenever there is a positive and negative, definitely the line of force or the potential difference which may take split between this. Okay. But you have been introduced a dielectric slab between the plates of the capacitor. So there only you may observe that the dielectric slab means there is a here random orientation of the charges are to be there. So that whenever if you place a dielectric slab between the here plates of the capacitor, because of here one is a positive, another is a negative, there is electric field is to be generated. Due to this electric field, due to the electric field here, the alignment, that means there is a induced charges which may turns towards the here opposite charges. That means here this is a plus here. Upper portion is a positive charge and lower bottom is a negative charge. So that these plus charges which are attracted toward the negative plate and negative charges which are attracted toward the positive plate. That's why here the alignment, you can see the alignment which may observe, okay, toward the positive and the plus alignment toward the negative. Is it clear? Okay. So next one, this is the displacement current. And whereas here electric field, so that you can observe direct line positive to negative, and also yes, this one. Next, whereas this one, inside the dielectric slab, there is a negative to positive. Okay. So induced charges you may observe. That is to be considered as a polarization. So according to the relation, B equals to Q by A, P equals to Q by Q dash by A, and by simplifying this, you will get the relation. This is very, very important. So what are the three vectors? Electric field strength, capital E, displacement D, polarization P, definition, relation F equals to Q. You feel the electric field strength associated with all charges, displacement is free charges only, polarization is polarization charges. Okay. General relation is D equals to epsilon naught E plus P. You need to remember this. So this is the figure, and from this figure only, you have to calculate the what is the potential. Go through this calculation. This is very, very important. Okay. So this we may conclude this today's class. And by coming classes, can go for the block 2 current electricity. What is a electrical conductivity, Kirchhoff laws, networks theorems. Okay. So by coming class, we will discuss the second unit. Okay. Important. Right. All the best.